Welcome to the last day of class. Hope everybody had a good semester. Let me remind you, we kind of do this laundry list theorem that I did last time. If you have a Noetherian ring, a kind of degenerated ornamental and B and A, some submodule. And then what do we have? We had C that was C is a submodule of A such that C. So C was some submodule A such that IB is contained in C. Right. And is maximal with respect to the property. And of course, we pointed out last time that the module IB itself satisfies this. It may not be maximal, but it satisfies this intersection property. Then I and A is contained in C. So we went through this last time, and this gives us statement called Krull if you look up Krull Intersection Theorem, there's different statements of this that are written different ways. This is the way I'm going to say it is slightly more general than what you probably see pop up when you first look at it. Let R be Noetherian. And I and R an ideal. Now let A be a finite degenerate R module. And B and let B be the intersection of higher and higher powers by n times A, then IB is equal to B. Okay, so let's go through this. So let's consider first the collection of submodules of A that contain IB. All submodules of A containing IB. I want to select C that's maximal with respect to the property that we had over here. So you might sort of smell a setup here. Let me point out that this can be done, using Noetherianness rather than appealing to the axiom of choice. So by the previous theorem, I and A is in C for some in the natural numbers, applying the previous result that we did last time. But since B is in I and A, this here, since B is in I and A, it must be the case that B is in C. And so, since B intersects C as IB, then it must be the case that IB is equal to B. And we have the conclusion of this here. Okay. Okay, so any questions on that? Okay, so here's another couple of auxiliary results that use sort of Noetherianness before we build up to Nakayama's lemma. Theorem. Theorem 607. Let R be a ring, I and R, an ideal and A, I'm going to specifically say A is a R module generated by n elements. And of course, another way to think of that is A is just some R module that's the homomorphic image of the n copies of all R. And X and R, an element satisfying XA is contained in IA. Then X and Y times A is equal to 0. From Y and I. Okay, so here's the claim. These are not terribly hard ones you do, but I always find that it's useful to take a little while to sort of get a picture in my mind here. So you've got a ring and an ideal, and you've got some n-generated R module. Now suppose you find an element X such that when you multiply X times A, it's contained in I times A, right? Then, where n is the number of generators, X to the n plus Y times A. So you should be able to find an element Y and the ideal such that x to the n plus y annihilates everything A. So, let's go through this. This is sort of, I think, reminiscent of kind of the way we attacked integrality. Let's suppose. Okay, so suppose we've got our A is our module generated by those n elements. So let's call it this way. So let's find suitable elements, y, I, j, and I. Such that XA, well, let's see, XAI. Well, because of this right here, this has to be any X times the ith generator of this has to live in IA. So I can write this way, YIJAJ. Right. So this means that X times any generator is a linear combination of these YIJs and I times the generators AJ. And this gives me right. This gives me the following system of equations. So let's see, because X minus A1 is equal to 0. I do that again, this is going correctly, don't I? Minus y 2 1 A1 minus x minus y 2 2 A2 minus y 2 3 A3 minus y 2 n n is 0.
You want that to be a plus sign before your parentheses.
Yes, I do. Thank you. I do. Yes. All the way down to two, 2. Right. Now, harking back to the earlier proof that we did with integrality, in matrix form, the determinant of a set matrix must annihilate all A, must annihilate all AIs. AI, hence, A, because if you kill each of the generators, you kill the whole module. And the determinant of this is a form x to the n plus y, with y and I. Of course, I haven't really multiplied this out, but of course, all these other, all these yi's are in I, and when you get the determinant, you get an x to the n, and everything else you can kind of bundle up in y. Okay, any questions on there? Yes.
I feel that these theorems are very technical, so are we trying to show something properly? Do we have an ultimate goal?
Yes, in fact, I'll show you one here as a corollary, and another ultimate goal is, Nakayama's one as well. The Krull Intersection Theorem that we gave you may look technical, but it can be applied to a number of special cases like integral domains in general, or local rings, Noetherian, and get some nice things. So for example, a consequence of the Krull intersection theorem is, right, if you have a maximal ideal, and, okay, here, the ring has to be Noetherian, right? But if you have, right, so if you have like, a local ring. See, what was it I wanted to say? So, let me get back to your question, but so one of the more, one of the applications really of, Krull's intersection theorem is when you're looking at domains or local rings and you're looking at, powers of, ideals, right? So if you have a, so for example, if you have a,
Like intersect, I n over all natural numbers.
right, yeah, that's right. So if you have a, that's what I'm trying to think of, it's not the power of the intersection. So if you have an ideal and, a domain that is Noetherian, or, in general, maybe not a domain, but it's, local, then when you intersect the power of, any ideal in there, intersect over all powers of it, intersect by, you get 0. Right, and that's something that's a little bit more familiar than, a little bit more familiar looking than Krull intersection theorem. But yeah, so let me give you a quick corollary to this. Let's look at theorem, 607 in the case where A is generated by a single element. I'm sorry, for the case x equals 1, let's do that. But R be a ring. I and R, an ideal, and A a finitely generated R module. Here I want to satisfy, let's not worry about the power. A can be generated by finding how many things you want. Let's let X equal 1. And so I have that A is contained in IA. Actually, right, so certainly, A always contains IA, doesn't it? Then this is immediate, from this result here. Let me point out that, of course, if you take X equal 1, then this condition is A is contained in IA. And of course, the other containment is always true. So this, I could have written A is contained in IA. Now replace X by 1. So what this means is if A is equal to IA, then A is annihilated by something of the form 1 plus Y, where Y is in the ideal. So it's annihilated by something that's outside of the ideal in particular. Um, Definition 609. Let R be, in this case, we've got a domain, an A and R module. We say A is torsion free. If the equation XA equals 0, implies X equals 0 or A equals 0. Okay. So does anybody know why we might care to restrict the domains here? Probably notice that I did say domain instead of just confirm identity. I mean, you could, on the surface of it, I mean, you know, I'm not asking you to criticize a definition, because you can make a definition whatever you want, but why would we care more about domains here, right? Why would we, you know, just kind of focus on domains for this definition?
Maybe you want R to be room free.
Well, so,
It's never true.
well, so for example, if you have a module, then the elements that are torsion, right, the ones that are torsion, so they're, they can be killed by a non-zero element, form a submodule in the domain case, whereas in the non-domain case, they don't. And also, torsion free is a little bit, so for example, if your ring has 0 divisors, right, if you have A times B equals 0, A is a bad choice. Let's say if you have X, Y equals 0, then if either X or Y doesn't annihilate this kind of clouds the definition a little bit, right? Because the 0 divisors can affect this as well. So that's why for now we can define things more generally, but we're going to focus on domains here. Proposition. let R be a Noetherian domain, and I a proper ideal. I and R, uh, let me emphasize a proper ideal. And a finitely generated torsion free R module. Then we intersect I and A, get 0. Okay, well, first of all, before I prove this, I love examples, as you all know. Because it drives everything, so. Can somebody give me a bad example that shows that I can't, I want to concentrate on finitely generated and torsion free. Can anybody give me an example of, oh, well, actually, listen. Explain to me why we need domain. Can anybody give me an example for an Noetherian ring with 0 divisors where this situation doesn't happen?
F times F, where F is a field, like element 1, 0, square it, or taking the power of it, just get itself.
I'm gonna steal your example and I'm gonna put it in more simple terms, because actually I'm gonna do let R equal C6. So here, I think we can all agree this is Noetherian, but it's certainly not a domain, right? And here you have the ideal just consisting of 0, 3. Notice that, of course, INA is now abbreviated as just IN, right? Because A and I are the same thing. Notice that it's I, right? Because what are the elements of, for example, I squared? Well, you've got 0, but you've also got 3 bar times 3 bar, which in Z6 is still 3 bar. So domain is certainly necessary. And this example is so small that domain is very necessary here. You can rip off this idea to see that you need a lot of the hypotheses here in general. Proof. Let's let B equal IMA. Applying earlier theorem, we have IB is equal to B, right? And by the previous theorem, so 1 plus YB some Y and I. But here what we have, here's where we use domain. Well, A and hence B is torsion free. Then either B equals 0. Or Y equals -1. Right? Because either B has to be 0 or this thing has to be 0 because the module is torsion free. But this one is impossible. No proper ideal has -1 in it. So that does it for that. Yeah, I think time will spell here. Okay, yeah, so I know I'm gonna finish this up here. All right. Let me give you the rather famous Nakayama's lemma. This is theorem 6011, I guess. What the content here is, suppose R is a ring and A is a finitely generated R module. Let R be a ring and let J be the Jacobson radical of R. Let me recall for you what that is. That is the intersection of all maximal ideals of R. It's bigger than the nil radical, which is the intersection of all prime ideals. In general, it's bigger because you're only intersecting the maximal ones. Suppose A is a finitely generated R module such that JA is equal to A. Then A is 0. Okay, so let's actually, of course, finitely generated is going to be very important for this. So let's go to the proof of Nakayama's lemma. So what it says is, if you've got a finitely generated R module, and the Jacobson radical is the intersection of all maximal ideals, if it's true that this times A recovers A, then A has to be 0. So in other words, you expect JA to be contained in A, right? If you had equality, then A had to have been 0. So let's prove this. Suppose A is A1 A2, AN. So it's finally generated. And suppose that, N is minimal. So in other words, what I suppose A is generated by N things, but cannot be generated by N minus one things, right? So this is a minimal number of generators we have here. We assume N bigger than zero and derive a contradiction. First note, that A is equal to this is equal to, well, yeah, that's right. J1, A1 plus J2, A2 plus JN, AN with JI in. Right? This comes from this hypothesis, because if I have A1 in here, then it has to be a linear combination multiplier from J times the generators here. Right? So I get this. Does anybody see where we might be going with this?
We can move over J1A1 to the other side.
Okay, so let me rewrite this. And how does this help?
1 minus J1 has to be.
That is correct. This is the magic of the Jacobson radical. That must be a unit. Right, because J1 is in every maximal ideal. So 1 minus J1 is in no maximal ideal, making it a unit, right? And what does this mean? Well, this means that A1 is in, well, actually, let's go this way. In fact, my starter condition is true, but I think it's a little bit clear to say. A1 is in the ideal generated by A2 because I can generate. Therefore, A is generated by N minus one elements. And there you go. So you see how the Jacobson radical thing came in pretty heavy handed there. Okay. So let me give this proposition here. Let R be Noetherian with Jacobson radical J. And A is a finitely generated R module. then intersection of I, or I'm sorry, that would be J in A is equal to 0. Proof. Let D equal set ideal. And apply Nakayama's lemma. In particular, what you get is B equals JB. And so B is equal to 0. So cogitate the details of that. That's pretty straightforward application. I am going to give you two more theorems for the course without proof, just to kind of give you a feeling for, oh, well, they're just, I think, a couple of cool theorems. One of them in particular concerns zero divisors in a Noetherian ring, and the other one is kind of an interesting result about prime ideals. So last two theorems of the course, theorem 611. Let R be Noetherian and A a finitely generated R module. Then there are only finitely many maximal I'm gonna have to explain this. I kind of got a little carried away. Then there are only finitely many maximal primes of A, and each is the annihilator of a non-zero element of A. I'll explain that tomorrow. And each is the annihilator of a non-zero element of A. Okay, so what I really need to explain here is what do I mean by a maximal prime of a module? Well, first, let me say, if R is a ring and then the set of regular elements that is non-zero is saturated multiplicatively closed. Right, so its complement, what can you say about its complement?
It's a union of prime ideals.
Right. In this case, the zero divisor of R is a union of prime. So the collection of zero divisors must be a set theoretic union of prime ideals. The primes maximal among these are the maximal primes for zero divisors. Generalize to Z of A, which is the set of R and R, such that, that annihilates some, R A equals zero for some non-zero. So this is the collection of, we call this a set of zero divisors on A, using that suggested notion. This is a collection of elements that kills some non-zero element. Now, of course, this is also the complement of a union of a saturated multiple closed set and is union of prime ideals, and that's what we need here, right here. And I will give you one last theorem, because I just think it's kind of nifty, and I challenge you to kind of look it over and prove it. What is this theorem? So let R be a commutative ring with identity, and I have a collection of the n ideals. These are ideals in R. And S is a subring contained in this union. S is contained in big one union. So you've got some subring in the loose sense that it's because obviously it can't contain the identity, is contained in the union of these. If at least n minus 2 of these ideals are prime, then S is contained in JK. Oh, so that's kind of interesting. So if you have a subring that's contained in the union of these, then if at least n minus 2 of these things are prime, then it's got you thinking one of them. So think about that. That was kind of a fun one to kind of think about over Christmas break for fun. Any questions?